Good morning and welcome to my stream. Yeah, the mic quality is good. So yeah, today's task. I've muted myself. I muted the wrong input. Okay. So good start. I have the wrong scene. This is the correct scene. Okay, perfect. So yeah, today's task of day 8 is playground. And the description is, equipped with a new understanding of teleporter maintenance, you confidently step onto the repair teleporter pad. You rematerialize on an unfamiliar teleporter pad and find yourself in a vast underground space which contains a giant playground. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they have suspended a large number of small electrical junction boxes. Their plan is to connect the junction boxes with a long string of lights. Most of the junction boxes don't provide electricity. However, when two junction boxes are connected by a string of lights, electricity can pass between those two junction boxes. The elves are trying to figure out which junction boxes to connect so that electricity can reach every junction box. They even have a list of all the junction boxes' positions in 3D space, your puzzle input. For example, this. And this list describes the position of 20 junction boxes, one per line. Each position is given as X, Y, Z coordinates. So the first junction box in the list is at X 162, Y 817, and Z 812. So these three, integer values. To save on-string lights, the elves would like to focus on connecting pairs of junction boxes that are as close together as possible, according to straight line distances. In this example, the two junction boxes which are closest together are 162, 817, 812, and 425, 690, 689. By connecting these two junction boxes together, because electricity can flow between them, they become part of the same circuit. After connecting them, there is a single circuit which contains two junction boxes, and the remaining 18 junction boxes remain in their own individual new circuits. Now, the two junction boxes which are closest together but aren't already directly connected are, after connecting them, since is already connected to another junction box, there is now a single circuit which contains 3 junction boxes and an additional 17 circuits which contain 1 junction box each. The next 2 junction boxes to connect are, these two values. After connecting them, there is a circuit containing 3 junction boxes, a circuit containing 2 junction boxes, and 15 circuits which contain 1 junction box each. The next 2 junction boxes are 431, 825, 988, and 425, 690, 689. Because these 2 junction boxes were already in the same circuit, nothing happens. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They would like to know how big the circuit will be. After making the 10 shortest connections, there are 11 circuits, 1 circuit which contains 5 junction boxes, 1 circuit which contains 4 junction boxes, 2 circuits which contain 2 junction boxes each, and 7 circuits which each contain a single junction box. Multiplying these together, the size of the 3 largest circuits, 4, and one of the circuits of the size 2 produce 40. Your list contains many junction boxes. Connect together the 1,000 pairs of junction boxes which are closest together. Afterward, what do you get if you multiply together the sizes of the 3 largest circuits? So, that is, I think quite the task. So let's open the puzzle input and let's open the straight line distances. Straight line distances here are just the Euclidean distances. So it's just in the vector. So in our example, it would be 162 minus 425 squared plus 817 minus 619 squared and 812 minus 689 squared. And these added together is the distance between between our tuples. So this is how we can calculate the distances. So you see two main parts here actually. The first is calculating the distance between all of these pairs, where I currently don't see any way we can get around that. Why would we want to get around that? Well, because that is quadratic. As for each triplet, we have to compare it with every other triplet. And we have to do that for everyone. So it's n squared. And yeah, I think it should be all right. And especially in Rust, that shouldn't be too much time spent with that. So, and then we have the question, what do we do with that? So I think we should store that in a map. Maybe let's go over to Visual Studio Code and I will prep our day 8 and then quickly sketch how I think we should proceed here. So let's first, do this, and this, and then we can remove you, and here we simply return a 0 at first, and the same here. Then we remove this, and I quickly jump over to our browser and copy in the test code. No, why am I deleting that? I don't want to delete that. So, and the result was 40. So then let's quickly add that to our module here. I may be a little bit tired by the mistakes I'm making. So day 8, and we have to import that, of course. And then let's get over here. So, and our position is another U size. Yeah, so what we have to do. First, calculate the distances. And all n times n distances. And then I would store them. I'm not sure if that is actually so smart, but we will see. I would simply store them in a vec of position with the distance. And then sort by distance. In this way, we can simply iterate over the first 1000. And we have to be careful here. We have to calculate all n by n distances and never store A, B, and B, A. So we have to be careful here that when we store such a pair, So A and B would be positions here, but we should only store one direction and not the other direction. Exactly, because otherwise it could be that we get duplicate distances here, and that could destroy the entire process. So now that we have that, we go by let's interject a little step here. Build group structure. What does that mean? So we need a structure to find the circuits. And let's maybe not call them groups, but circuits. So the circuit structure. Let me quickly check. Ah, that's how it's spelled. Okay. Yeah, the circuit structure. Here we store I had a good idea how we could store that. So we need two data structures here. We first need a set of sets of positions, where the inner set here is our circuit. So circuit type circuit is equal to a set of positions. And then we can use that here. This is kind of pseudocode, but I kind of already write it how we have to do it in Rust, just to be closer to what we actually need. So this would be the owning structure, because we have to have a single owner for what comes next. Next, we store a map of position mapped onto reference of circuits. Why is that important that this is a reference? What I want here is that each position knows in which circuit it is, but the circuit value could be in this map multiple times. So when that is the case, we cannot have we cannot have the positions own the circuit, because otherwise we would have duplicate ownership, and that is not allowed. So we need a second data structure, a set, to keep track of it. So this is then our circuit structure or circuit structures. We have the set, which is the owning structure, and the map, which is our lookup table. And then we iter over our sorted distances. And what we do is we then get, this should not be simply a pos, but this entire structure should be pos. Wait. Pos distance. So we need two positions here actually. So iter over the distances, pos 1, pos 2. We don't actually need the distance here. And what we have to do now is we have to look up in our map to get the two circuits of these two distances. So map, let's just do it. Map pos 1. This would be C1, and then we have C2 for those. Then we remove from set of circuits C1, C2. Join C1, C2, and add to set of circuit. And then let's call this into CJ for point, add CJ to set, and then map pos1 is equal to a reference onto CJ, and the same goes for pos2. Now we don't have duplicated ownership, and we have stored our circuits. So now when we are done, we have to find the largest circuits, and for that we can simply, so the finisher would simply be yeah, it could be yeah, let's just say get 3 largest circuits from set of circuit and multiply lengths. And that's our return value. So this task has multiple steps, but I think they are all pretty doable, and I think this should actually lead to a solution, and I hope to a solution that finishes in a reasonable amount of time. So let's maybe put this, maybe let's copy this here and use it as the description for our method. And then let's go here. And let's first pass our input. Split on \n map onto 9 and split comma so vals map. I mean, we could already say here map val and say val.parse, and we take our num type here. Actually, we need them as U sizes. And yeah, so that would be, then we can say collect, but actually map one more time. Here we simply say unwrap because we wanted to panic. It doesn't work. And then we say num is what? Split on semicolon. We have, yeah, okay, no, we cannot map here. That's not what I wanted. Now we have the vector of vals, which is erroring out probably because we didn't specify the type here. It would be a vec of U size. And then we simply return val0, val1, and val2. Yeah, because there is no val, there's only vals. Now it's kinda happy. So, positions. Those are all our positions, and we collect them into a vec of our pos type. So now we have our positions. Our pos type was here, the usize, and our num in the end will be I64. So this is actually the pre-processing. This is actually still above this. So now we have to calculate all distances and store them in this vector. Pos with dist is a vec macro. And then we say for d in positions, let's call it pos1 in positions, and for pos2 in positions. If we say iter and enumerate, we actually get the index and the positions, and then we can say skip the first I plus 1. And then we can say, now we need a Euclidean distance function. Or let's just call it distance, and this is pos1, which is of type pos, and pos2, which is of type pos. And this simply returns I64. Let's call it num. Actually, it can also be U32, but let's just keep it like this. And then we have to say that we want the sum of pos1 at 0 plus pos1 minus, and the result of this should be raised by the power of 2. And we have to add those together. Yeah, let's, this will probably be a float 64, I guess. What's your problem here? Expected F64 found U size. Why would you be? Okay, because subtracting those. No, we cannot subtract them like that. Let's make a function and call it. Let's just call it term. And then we have X U size or X1 U size, X2 U size. And then we simply do what we did here. X1, X2 raised by the power, but now we need to say here as F64, as F64 raised. There's a method powf with a similar name. Yeah, then maybe let's say those are we want them as I64s or I32s. Doesn't really matter, they will be too great. And then we get an I32 back. Yeah, I mean, we can only get integers here, of course. That would be all right, but we needed the possibility to go negative here. And I think an I32 will be all right for that. We actually can only have integer numbers. We cannot have floats, so it doesn't make sense. What I wrote here first. And then we can simply add this term with this term, and here we say 1 and 1, and this should be pos2, this should be pos2, this should be pos2, and then this is 2 and 2. Here we have the term, we don't need to erase this now. And this is also a term, and we can remove this power, and now this should be all right. And what's the problem? Hue size is missing. Ah, I have a minus here instead of comma. So now this is now all right. This is now a distance. We could probably optimize this function, but let's keep it like that. It should be all right now. So then we say distance of +1 and +2, perfect. Actually, we can make those, no, we need them dereferenced later anyway, so let's see if we can dereference them here. We actually can, so then we have our D here. So, and then we simply say, let me think real quick. Yeah, I think we need a temporary data structure, definitely. Let's maybe make another scope here. And let's make a hash set real quick of pos and pos. The reason for that is that we can store. What's the problem? Remove the unnecessary generics. Okay. The reason for that is so we can look up if we already added this. So if added as contains, so it cannot contain pos1, pos2 because we can never encounter both twice, but it can contain pos2, pos1. And in that case, we simply continue. Otherwise, we calculate the distance, then we go ahead and say pos with distance, push, pos1, pos2, and the distance. And we say added dot insert +1, +2. So what's the problem here? Expected reference, okay. Makes sense. So pos with distance must be mute, as well as added must also be mute. So now added is simply for this. So outside of the scope, added is dropped. And we simply have pos with distance, which is what we wanted. Yeah, but you can actually shorten this by saying pos and pos here. So we haven't sorted it yet. We could immediately sort it here. Is there a sort by? Yes, perfect. Ah, it's not how I thought it would be. It's L1 and L2. Yes, and then we have to say L1 dot to dot. What do you need in ordering? So we need some compare. I think it's, yeah, it's just CMP and L2.2 as reference. So now this should be sorted. So sorts in ascending order. Yeah, perfect. So the first one is the smallest. So next we need to build our circuit structures. Let's first define our circuit structure, how we did here. So this is actually a hash set of pos. This is our circuit. So then let's do a yeah, we simply have to iter over the positions for pos in positions. We create a new circuit. Let's actually use a reduce here. Position start fold, sorry, a fold. And we iter a new map. We create a new map, and then we have our accumulator and we have our element. And then we simply say accumulator dot insert. Aren't you sure what the accumulator is? The new function is not generic, but you are generic. This would be pos onto. No, this would be. We simply need the set here. Maybe we can create both collections at once. Yeah, that sounds good. So we actually make a tuple for our accumulator. The first is the set of circuit. And we have to do it like this, I think. Set, of course, doesn't exist. That one is just hash set. And then we have our map of pos onto a circuit reference. We also need to create that. Then, of course, we cannot insert here. Yeah, map doesn't exist either. It's also a hash map. And then we have to say that our accumulator, we don't need the mute here. This is actually the owning collection and the table. Let's call it like that. So there's no accumulator anymore. For the owning collection, or we say new circuit, circuit new into the circuit. Yeah, a hash set, exactly. Into C we insert. Now our element. We have to make this mute for that. And then into the owning collection we say insert C. You have to be mute. And then for the map, I mean, in the end, we have to return own and table again. And then in the map, we simply say table insert. The key is our element. And this is a reference to C. But we probably have to change that a bit. So yeah, we want to dereference this here. Into C, we want to insert the element, definitely. The method insert exists for struct hash set useset, but trait bounds were not satisfied. The following trait bound here were not. Oops. Hash set doesn't satisfy hash set use hash. It doesn't have a hash. We cannot have a hash set for it, I think. Yeah, I bet that's the problem. I mean, we could use a vector. Will push at least return a reference? Push doesn't return anything as far as I can see. Yeah, it does make sense. So the problem is now that C was moved. Yes, of course. But what we can say is on last unwrap. And the table has to be mute as well. And cannot return value referencing local variable own. Why would own be a local variable? I'm not overriding it. Cannot return value referencing local variable own. Returns a value referencing data owned by the current function. Because no, I don't see it right now. Should it be a box? We probably need a box. Yeah, but we cannot wrap the box like this. Then it's... let's actually start like this. This is owned. So we can here say that we start with init. Can we borrow that? No, we cannot. Then we actually don't need default here. We can simply iter over the positions. So then we have to say this is the owner, this is the table. Then we don't have to dereference the element because it is already dereferenced. Then u2 must be mute. And now own cannot borrow own as mutable because it's also borrowed as immutable. So the problem is the own last. Let me think. Yeah, I think there's no way around doing this work twice right now. So we can say that, and then we can say for C in own iter then this becomes element because I said own here. This is the element, and first call into iter first, iter last, unwrap, clone it. So now we have our table. Okay. Hard work, but it's done. So now we need to iter over the sorted distances for we have pos1, pos2, and distance for pos1, pos2, and distance. In pos with distance take 1000. I'm not sure if this throws takes n yields until n elements are yielded or the end of the iterator is reached. Okay, whichever happens first. Perfect. Let's maybe extract that to a constant. And take limit many here. And then C1 is equal to map at position 1. So yeah, C1 is table at pos1, and C2 is table at pos2. And then we say own dot remove. No, because it's not a set, we cannot simply remove it. I thought we could use a set, that's why I thought we could simply remove it. Capacity, no. I want to take the first where. Get, yes. Is it also we need partition point, no pop if. Oh, pop if sounds good. Removes and returns the last element from a vector if the predicate returns true, or none if the predicate returns false, for the vector is empty. The predicate will not be called in that case. So we have to pop the C here where C is equal to C1. And then we can say unwrap and let C1 is equal to the owned one. And then we do the same for C2. And the problem is immutable borrow occurs here. Own as mutable cannot be borrowed because it's also borrowed as immutable. Immutable borrow occurs here. Okay, but that immutable borrow can already be dropped. So that shouldn't be cannot borrow own as mutable because it's already... No, it doesn't matter to it that this is already dropped. So maybe when we make this a function, right, fn create table. And then own is a reference to... Where did I steal it from? Stole it from here. It's a vec of hash set. Vec of circuit. So in table, we create table here simply and return the ownership. So then we can, where was it? It was here. Create table from own reference. You still have a problem because cannot borrow own as mutable because it's also borrowed as immutable. But shouldn't this immutable borrow be already... because... yeah, that makes sense. Okay. The problem is that we borrowed the elements from set into the hash map as a reference. And the compiler cannot be certain that we are removing the correct reference here. So the compiler won't let us do this, because otherwise it could be that a value is dropped that is later actually used. So do we... I think we simply make the set extraordinarily huge and add every new set to it. So we don't do a pop. We simply do a C1 join union. We union those two. Can we say take drain, no, extract entry, extract if get remove. Yes, remove is what we need. +1, unwrap. Same for +2. Huh? Where does pos come from? You have to be mute. Where the heck does pos come from? It just accepted pos and I'm confused because pos is No, it doesn't exist. Okay, don't know why it accepted it. Okay, so we have the union. We remove those two from the table, and then we say this is our union, which should be now an owned typed. Okay, we can collect that again into. Is that a circuit? Yes, it's a circuit. Into a new circuit. Value type hash set usize cannot be built from iterator of and usize hash set. Ah, of course, because we have to collect it into a hash set of circuits. And before that, we have to take. What? C1 is a hash set of usizes, C2 is a hash set of usizes. When we union those two, this should return, in my eyes, not a hash set of usizes. Okay, if we say dot map, what type is element? Element is a usize. That makes absolute sense. Then we can simply dereference it here. And then say collect into hash site circuit. Because the circuit is already the hash set and this was correct in the beginning and yeah, okay, no. Let's do it like this. It's fine. Okay. And then we say table. Then we have to add this to our collection again. So own.push, and this will probably fail. Because we cannot borrow it mutable here. Because it is also borrowed as immutable. This is a problem. I didn't think about that. I think we need to make this super inefficient and don't have this table. Yeah. I think we cannot work with the table. That is the problem here. Because the table cannot take ownership, and without the ownership, this won't work. So we say now own first. There's no first where. And then maybe filter s. We actually have to remove where this is true because we need that. But we can only remove with an index. So performs the indexing. Ah, okay, this is just the indexing operation. That's not what we want. Yeah, we probably have to do iter enumerate find. Yes, that's what we want. That is actually equal to first. So find, and then we have to say the L is equal to +1. Because we have the index in here as well. Contains +1. This should be it. Yes, okay, so of course we have to check if the set we have actually contains +1. And this would be the container for this. Let's unwrap, because this will always exist. Then we remove at idx and c. No, we don't have to remove yet. Let's first check the same thing, but for the other container, because this could actually, those could be the same elements. So you are C1, you are index 1, you are index 2, you are C2. Yes, we don't need this, we don't need this. Here we unwrap, here we unwrap. Okay, so and now if C1 is equal to C2, we say on.remove at index 1, and else we say on.remove at index 1 and on.remove at index 2. Now both are removed, and then we can actually say C1.union with C2. Wait, removing this does return the element. Okay, so we can say C1 is this, C1. Let's C1 is this, let's C1. Let's C2. But actually, if they are equal, we don't need to do anything, because we can simply continue in that case. Because we don't need to remove or add anything, because they are already in the same collection. So we only have to look at this case here. Here we have to union those two. And then, yeah, collect them in a circuit, and then push that new collection. These two were already removed, so this is fine. And here's a problem, because we do not use C2. Why don't we use C2? Pos2. Because here we have to find that. Use an underscore here. Let's write a function real quick. own is a reference to a circuit. Is own a reference to a circuit? What is own here? A vector of a reference to a circuit. Back like this, and pos is simply pos. Can be a reference of pos, that's fine. Your pos. And then we can say exactly this. Maybe this was unnecessary as we already wrote this, but I wanted it anyway. Yeah, own and +1. And the same for you. So this works, or should work. So now we only have the set. It is more inefficient because we always have to iter over the entire vector, which is of course not great. But in the end, we can still say here that we want, yeah, simply what we wrote here. Own dot sort by, yeah, we got C1, C2, c1.len.comp.cmp to c2.len as a reference. Yes, and yeah, now this is sorted. Then we say own dot reverse, or we say iter ref take 3 fold. Can actually use reduce here, that's better. Accumulator next, back times next. Because we don't actually need sort by here. We can, as we only care about the length of our circuits here, we can actually say c.len, and then we can simply do a sort. We have to do an iter here first, then we have to collect those C lengths, C lengths dot sort, and then C length. This is a vec of size. We can make this owning. No? Mismatch type. But you're both use size now. Consider borrowing. We need to fold here and say 1 and then this works. Okay. And this is actually our return value if we simply say, yeah, you are already an I64, and then we can use you as an I64. Because it's a reference. And now this works, and cannot mutate immutable. Yes, finally. So let's check if that even works. It errors out. Panic. Panics here? Home.remove. Where? Oh. Of course, no. We cannot do it like that. If we do it like that, these index issues. The problem is if we remove this, then IDX2 can be at a completely different position. So we have to remove the unwrap here, fix the return type. Then do the unwrap here. Do this here, and then let's say here. Match. If it is none, then we simply have to insert C1 again. So we say on.push C1. And if this is not the case, then we can simply return, oops, I simply quit. Then we can just return the S again. This, of course, doesn't work because now the return types are different. But we can make a break here. And then we can move the semicolon here, add the semicolon here, and now it works. Yeah, because then we break, which is equal to the continue we had before. We don't have to check equality because they aren't equal. Yeah, we don't need you, we don't need you. We could actually, yeah, never mind. Let's first try it like this. That is an empty test. That test, of course, will work. 6, but we expected 40. Let me check the task real quick again. The task set in the end. What do you get if you multiply together the size of the 3 largest circuits? And here we multiply 5, 4, and 2. Then we have to use the debugger. So let's check here. size 17. 3 and 2 are the only sizes we have. That shouldn't be the case. Why is that so? Let's rerun this and let's check here. And maybe we make a split view. Like this. So, and now we have to check here. They said we have the first is 162.817. So pos with distances should return us. That is correct. Okay, so this will be the first element. Then what is the second? The next would be 162.817.812, yeah. And 431.825.988, yeah. And then after connecting them, since and the next are 960 and 85, 906, 360, 562, 805, yes. So I think our Euclidean distances are correct. 431, 825, 988. Yeah, this seems completely all right. So calculating the distances is not our problem. At least we found that out. That is something. So the problem is in here probably. How long is that list? Don't say it's over one. No, it's 190. So we have to go over the entire list. So let's check the logic here again. Sorry, I'm going back to the full screen again. So pos 1. Own iter, enumerate, find where the circuit contains this position. Then we have that here, and then we remove that. And then we can we check if we still find something that contains pos 2. And if not, we push C1 back, because then both already were in the same circuit. And otherwise, we also remove index 2. Then we have C2, C1 and C2. We map them together, collect them in a circuit, and then push them. Seems all right to me. So let's see what the problem is here actually. Okay, let's skip the loop for now. And let's actually look at own. So down here we have one with 3, one with 2, and one with 1. So why are there only 3 here? So in the end, there should be 11 circuits, but we have 17 circuits. I think there was a point where there were 17. Here I see 15 circuits. 18 junction boxes. But what could be the problem here? I'm really unsure. So we get all positions. We have to assume this is correct, because if this is wrong, this cannot really be wrong. I mean, we have 20 positions. That should be right. So we have 20 positions. We get the distances. We checked it. The list was correctly sorted. That was all right. Then we have this table here we don't need. This doesn't make a problem, but it annoys me. So then we go over all positions and we insert a circuit for each position. So we sorted them. Now we iterate over these distances in the correct order. Yeah, we can also check if we have the correct order, but the order shouldn't... No, the order doesn't matter in this case. The order is irrelevant actually, because we are iterating over all distances. We will eventually look at every position with their distance, because we are taking all 1000, so the order wouldn't even matter. So what is the problem here? I guess the problem needs to be that somehow we are always ending up here, right? Because if we don't end up there, then it should unionize, and then there shouldn't be a problem again. So 431. Let me quickly check. 431. We have the next two junction boxes are already in the same circuit. That's exactly the case they are documenting in the test cases. Sorry that I'm not splitting right now. We have to jump so often. I'm going to the split view again. No, that's not what I wanted. Now everything is breaking. Okay, this looks all right. So here we see we have 431, and that's actually this case, already in the same circuit. Nothing happens. That's exactly what we have here. Nothing happens, just like we wanted it to. So break. Oh my yeah, how can nothing happen afterwards if we simply break out of the loop as soon as we hit this simple case, which... Yeah, okay. Yep. Test completed. No. Test panicked. Okay. Because we only have 20. Okay. I mean, we can simply debug again, right? Not like this, please. So. Okay. So what are the lengths? Huh? So everyone joined with everyone. Mm-hmm. Let's maybe check again. Ah, sorry. What they are saying here. Maybe I overlooked something. Maybe I misunderstood where we should stop. After making the 10 shorted connections, there are 11 circuits. One circuit which contains 4 junction boxes, 2 circuits. Yeah. I misunderstood when we should stop. That is the actual problem. That makes a lot of sense. So instead of let's make solve A for test. Which is a use size, then that works. We of course also need the input. And there's the limit. And we remove the semicolon here. So for test now also returns an I64. And then everybody's happy. And here in the test, we can say solve A for test and insert 10 instead of 1000. Run the test. And now the test actually finishes. So then let's go to the main, run this, and it panics. No such file or directory, of course. I didn't make a file for day 8. So then let's go to the main again, run this. Attempted to multiply with an overflow, okay. So not in the text files, but here we have the star. Here the multiplication must occur here. Wait. You multiply with an overflow when you take 3? Damn, do we need an I-128 or what? My program isn't even capable of... my infrastructure isn't laid out for that. Solve A, solve for a test, yeah, okay. Makes sense. Power. We raise by the power of 2 and that gives us an overflow. Okay. Then let's replace that with num. Then we have a problem up here because distance is not num. And let's try again and pray. This time it works. Okay, then let's go over to yeah, AOC, put that in and pray that it is right, and it is. Perfect. So let's quickly check task 2, but I think we have to postpone that. The Elves were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they are all in one large circuit. Continuing the above example, the first connection, which causes all of the junction boxes to form a single circuit, is between the junction boxes at 216, 146, 977. The elves need to know how far these junction boxes are from the wall so they can pick up the right extension cable. Multiply the x coordinates of those two junction boxes. What? Continuing, okay, ignoring the limit. The first connection, which causes all of the junction boxes to form a single circuit, is between the junction boxes at 26146, okay? The elves need to know how far those junction boxes are from the wall so they can pick the right extension cable. Multiplying the x coordinate of those two junction boxes produces continue connecting the closest unconnected pairs of junction boxes together until they are all in the same circuit. Okay. So we have to find the last two so that the size... Yeah, okay, I get it. So essentially, we don't limit here, but we break as soon as quickly hold that thought. We don't need a test separation here. We can simply we don't have a limit anymore, so there's no need for that. Simply paste that over, remove the limit here, and let's say if own.len is equal to 1, because then we only have one circuit left, then we break, but we don't only break, we also, what did the text say again? Sorry, changed to the wrong screen. It said multiply together the x coordinates of the last two junction boxes. So there. The last two junction boxes were now C1 and C2. No, that's not right. Pos 1 and pos 2. Okay. Pos 1 dot 0 multiplied by pos 2 dot 0. And that is our return value as I64 and as, or let's say as num and as num. And if we reach this part here, we simply panic, because this should not be the case. Because if that happens, something went completely wrong. Quickly switching over and grabbing the expected result. We run the test, pray that there is... yeah, of course. We run the test again, and we see that B finished. Perfect. So we can actually run the main. Yeah, takes some time, but if we go over to here, post that in. It's correct. We did it. It's so nice when the second task is so fast. Very, very nice. Okay. I have to get going anyway. Yeah, so I will load up this video later on YouTube. I don't have time right now to finish that. Yeah, so if you're watching it on YouTube, thank you very much for watching. I hope you had fun and learned something. And maybe I see you tomorrow in the stream at 7:30. And otherwise, yeah, see you in the next video. Bye.